Now, this section was supposed to be all about statistics, but so far we've done very little with data. But we're going to change that now, because this section is all about the characteristics of data sets. So if we start with a list of data, usually the thing that we're most concerned about is finding the center first. The center is usually referred to as an average, and if I told you to find the average of a set of data, you would find what's more specifically referred to as the mean. The mean is what you find when you add them all up and divide by how many there are. Now, because all measures of center can technically be called an average, we want to be careful when we use that word when we're specifically talking about statistics. Because in reality, the mean, the median, and mode are all three averages. The median is the value that's in the middle, but it's not just in what happens to be in the middle. It's the middle value if all your data is sorted in order. So when you have your data sorted in order, the relevance of the middle value is half of your data is more than that value, half of your data is less than that value. So the median cuts your data in half, the lower half and the upper half. If you have an even number of values, you won't have a data value in the middle. In that case, the median is between the two middle numbers. So you find the mean of the two middle numbers, and the median will be a dividing line that's directly in between the two middle values. The mode is the value that occurs the most often. So it's your most popular answer or your most common answer. If you don't have any repeats in your answers, then you have no mode. So you have to have some repeats. If you have multiple repeats, the mode is the value that occurs the most often. And if you have a tie for first place, if you have more than one value that occurs the most often, then your mode is just all of them. You can have 2 modes, you can have 5 modes, you can have 10 modes if your data dictates it. So I have a list of prices for air conditioners of a particular model, and I want to find my 3 measures of center. So I start with the mean. And the mean is where I do arithmetic. It's my arithmetic center. So I add up all my data values and divide by how many there are. And since I'm talking about prices, I will round my answer to dollars and cents. The mean price of an air conditioner, this type, appears to be $512.86. My data is all out of order, so if I want to find the median, I need to rearrange it. So let's put my data in order from lowest to highest. Then to find the median, I have to literally find the one that's in the middle. And that would be my 470. The mode, if I have one, is the data item that repeats the most often. I do have a repeat, 440 there. 440 happens 2 times and it's my only repeat. So that's my mode. Now I have 3 different numbers here. All of these are supposed to be telling me a center. My 470 is literally in the middle. My 440s, those are my most popular answers. So that's the answer that occurred more than once in this case. But where's my mean? My mean is all the way out here. It's almost to the end of my data. Now the reason my mean got pulled away from my center, which this is my center, my mean got pulled away from my center because I have a really large value here on the end. Look at it. If I go along 420 to 440, that's a leap of 20. This one stays the same. Then I've got a leap of 30 and 20 and 20. But to go from this data value to that one, there's a 340 unit difference. That's a big gap. So there's something called an outlier, which is just a value that looks unusually large or unusually small when you compare it to the rest of your data. 840 appears to be a strange value to be with the rest of these. So what you can do is, if you have an outlier, you can delete it from your data and you can recompute your mean, your median, and your mode. So why don't you pause this recording and find a new mean, median, and mode for this data. Now what happens here? When I recomputed the mean without the 840, I got $458.33. If I put my data in order again, I don't have a middle. I have two data values in the middle, and my median should be right in between them. So I take 440 plus 470, divide that by 2, my median turns out to be 455, which is right between my two middle data values. That's my dividing line between my high half and my low half. And the mode didn't change at all. Now, if I look at where these fall, here's my 455. 458 would be just slightly higher than that, and the 440 is right next to it, right below it. So my measures of center are all three in the center now. Outliers mess that kind of distribution up. If I compare what they used to be, this is with the outlier, this is without. These are definitely closer together if I don't have the outlier in there, but let's look at the differences. The mode didn't change at all. The median, that changed slightly. It changed by like $15. But look at the difference in my mean. My mean is the one that was pulled way out to the right with that big 840 in there. The mean changed by $54.53. That's a significant difference. So the moral of this story is your mode is not affected by outliers at all. Your median can be affected a little bit. But your mean is definitely affected by outliers. And it doesn't matter whether it's an extra high value or an extra low value. It will disrupt your mean from being in the center with your other values. Another thing we want to talk about is the shape of distributions. And it doesn't matter whether we talk about the shapes of a histogram or if we curve them off. A histogram is the bars, if you recall. The curves, they happen when you have just a different type of graph than what we're usually making. Now, if I look at a graph, and let's look at it like a histogram so we can talk about the bars. How do I know what the mode is of a histogram? Well, a mode is the answer that occurs the most often. In a histogram, how often an answer occurs dictates how tall the bar is. So the mode is the tallest bar. I can find the mode from a histogram because it's the tallest bar. If I have a distribution where I only have one peak, one hump, one highest bar, that's called unimodal. Now bimodal, when we talk about distributions, it means a little bit different than just having two modes. If I look at this second graph, I still only have one tallest bar. Technically, if I was listing in numbers what is the mode would be the value of only this bar. But what happens with my distribution? It reaches a peak, but then it comes back down. It comes back down significantly, and then it goes back up again. So this is another peak, even if that peak doesn't reach the height of the first peak. This is like a double camelback. If we have that, it's called bimodal. Usually the reason for a bimodal distribution is two different populations graphed as one. So we would have this population over here, which has one most common answer, this population over here with this most common answer, and perhaps a small overlap in the middle of the two populations. Now, it's also possible for a distribution to have no peaks. What that means, if you think about a histogram, it can mean that the whole graph goes just straight across. But that wouldn't usually happen in real life. In real life, you might have bars that just seem to repeatedly kind of go up and down, so that when I look, there's a general height to the bars, even though they all might not be exactly the same, because it's rare for samples to turn out perfect. So we have some examples, and the question is, how many peaks would you expect for each of the following? Now, the idea is that you're not going to actually make a graph, but you want to think about what the graph would look like. If I had the heights of all women at a college, what I'm trying to think about is, if I was making a graph of that, would I expect women to have one most common height, a height that most women were near, and if they weren't exactly that height, most women would be real close to that height, and the people who were a lot taller or a lot shorter than that height, there'd be fewer of them. If you think that a distribution is going to have one most common value, that would have one peak in the distribution. Now, what's the difference between measuring heights of all women and measuring heights of all students? There's probably a different most common height for men than there is for women, correct? So I would have one peak for the men, and I'd have a separate peak for the women, and as I got away from both of them, they would probably both come down somewhere in between. So this would be two peaks. This would be bimodal, a mode for the men and a mode for the women. So security numbers. Social security numbers are supposed to be random, especially those last 4 digits. So even if I took a sample of 100 people, I'm probably not going to have exactly the same number of people who had 0 and exactly the same number of people who had 1. But it should all be fairly similar. This would be no peaks. which we call uniform. Uniform is a distribution with no appreciable peaks. Now, if I have a distribution, to talk specifically about the shapes, I can tell by looking at this that the middle bar, that is the mode, because it's the tallest. Now, the fact that this is symmetric, which means the graph looks the same to the left as it does to the right of that center, the median is also that middle bar. Oops, IAN. And it will cut the graph in half. Half my data is to the left, half my data is to the right. But it's not only that. If I actually did the math, I would find out that my mean is also in the same bar. So symmetric, the mean, median, and mode are all the same, and they're right there in the middle. If I had any outliers to this data, I would have to have a very small value and a very high value to kind of balance each other out. Not one or the other, I would have to have one of each. Now, if I have data that's left skewed, this is my mode, because my mode is my tallest bar. When I have my tallest bar toward the right, which this is kind of a bad example. I could have an additional bar or two to this side. But I have the lowest data values, or the lowest frequency data values are over here. This is left skewed. Because what happens is if this is my mode and my mode is no longer in the middle, it's because some of this data has been pulled over to the left. What that means is that I don't know exactly where it is with no numbers, but my median would have also gotten pulled over to the left, and my mean got pulled further to the left. So left skewed tells you that the data kind of got pulled out. Just imagine spreading some cards further to the left. If I kind of fan those out a little bit, when I pull my cards that way, I'm actually pulling my median over a little and my mean over a lot. And the direction they're going is the direction I sort of just slid my cards, and that would be to the left. I don't know if these values down here on the left are outliers or not, but if I did have any outliers, they would definitely be over here. Right skewed, everything I said, just the opposite. It's like, here's my mode, and I swipe my hand over the cards, and I have pulled them to the right. When I pull them to the right, I pull my median to the right, and I pull my mean even further to the right. The right skewed tells you which way you've pulled your mean, which direction you've pulled your mean in. If I have any outliers, they would definitely be high values. This is kind of just a picture of what happens to the mean, median, and mode if you have the different distributions. Just because they're curves, you can picture them as the bars we had. Your mode is always the tallest part. So if you find the tallest part of the curve or the graph, that's your mode. If your graph is symmetric, the mean, median, and mode are all right there together. If you're talking about a right skewed distribution, if this is your mode, the median is always in the middle and the mean gets pulled the furthest away from your mode. The mode is always your tallest bar. The median is in the middle. The mean gets pulled away the furthest. Now there's actually a question on the test or on the final, and I'm not sure which, that has a picture similar to this, where you have to identify in this type of distribution which is the mean, which is the median, and which is the mode. So you need to know what order those come in. Variation. Variation has to do with how spread out our data is. So we've looked at where the middles are. We've looked at how things might get shifted to the left or to the right. This time we want to talk about if we have our middle, which I kind of missed there. The more spread out we are, the more variation we have. Variation doesn't talk about a bunch of ups and downs. It means how spread out are we. So if my data only goes from here to here, that's a low variation. This is more spread out because it covers that span of a distance, and this is more spread out than the other two. So if I want to talk about variation, the thing that I'm thinking about is, okay, in the Olympic marathon, the people who are running, those are like the best of the best. Who's running in the New York marathon? In the New York marathon, we've got just the people who want to participate. Anybody. So it could be people who can barely walk, on crutches, with their dog, and the people who are training for the Olympics. Anybody who just wants to do it can do it. In the Olympics, if I thought about the span of time for the Olympic marathon, hopefully these times are much closer together than the times for the people in the New York marathon. In the New York marathon, I would think there would be people who took 12 hours because they just want to do it. It's just a goal. But it's not the best of the best. It's amateurs and professionals. So how would you expect the variation to differ? Olympics would be low variation, and the New York Marathon would be a high variation. Time's much more spread out. One way that you can think about measuring variation is by doing a 5-number summary. 5-number summary has 5 numbers in it. 3 of them we're already acquainted with. The low score and the high score, obviously we've talked about the minimum and maximum before. These data are conveniently in order, so the minimum is the first score and the maximum is the last score. Another number we're familiar with is the median. The median is the middle number of a data set. So if I count my data and I find my middle is this 7.2. Now remember what a median does. It cuts your data in half. Well, what I want to do now is I want to look at my 2 halves, my bottom half and my upper half, and I want to find the median of each of those. So I want to cut half of my data in half, which actually means I want to cut my full set of data into 4s. If I look just at my my lower half of the data, if I look just at these numbers here, the middle of my lower half is 5.6. If I look just at my upper half, the median for my upper half is 8.5. The symbol with the Q's, Q stands for the word quartile. Quartile means 4th. So Q with a subscript 1 stands for the first quartile. Q with a subscript 3 stands for the 3rd quartile. Technically, the median is the 2nd quartile, but just like we don't call the fraction 2/4 2/4, we change it to 1/2 because 1/2 is a stronger statement than 2/4. We don't call the second quartile the second quartile, we call it the median because that's a stronger word. Now, if I have my 5-number summary, I can make a graph called a box and whisker plot from it. To make a box and whisker plot, I should have some kind of number line, and I don't actually use my number line to put the graph on. It's more like a ruler, so all my pieces and parts stay proportionate. If I start, the first part of my box and whisker plot is the whisker. The whisker goes from my minimum to my maximum, so it's just a line segment that's going to go from 4.1 all the way up to 11. That's my whisker. The box is going to go from Q to Q. So the box is going to have the whisker going right through the center of it. It's not going to sit on the whisker. It's not going to hang from the whisker. So if I want to go from 5.6, that's from approximately here, to 8.5, that's about here, and then I connect it up to make a box. The median cuts the box into 2 pieces, not necessarily 2 equal pieces, but it will segment the box. Now the significance is 25% of my data is in this region. 25% of my data is in the left-hand side of the box. 25% of my data is in the right-hand side of the box. And 25% of my data is in that right whisker. The position that shows me, what that tells me, is if I have an extra long whisker, or if one side of the box is bigger than the other, my data is more spread out in those areas. Any area that seems more compact compared to the other ones, that's where my data is more clumped up. So you can kind of see how your data lays from from the beginning to the end, from the smallest to the largest. Where do you have your major concentration of values? Now, the 5-number summary kind of shows how our data varies. It's kind of another picture of a distribution. Now we're going to talk about numbers that will tell us the measure of our variation. One measure of variation is the range, which is just the highest value minus the lowest value. That's usually not a bad way to start, but the problem with the range is it only takes the highest and the lowest value into consideration. Think about our first data set where the highest data value was actually $340 more than the next highest. That would give us a range that was a little higher than it should be, than if we left the outlier out. Standard deviation, though, this is a very popular measure of standard deviation. We're not going to get into the statistics of it. You have to take statistics class for that. All we want to say is this is a measure of variation that when you compute it, it takes every single data value into an account. So it's it's not totally immune to the effects of outliers, but outliers have less of an effect on the standard deviation than they do on the range. Now we're just going to use our calculator to compute the standard deviation and not worry about the rest of it. So we're going to look at this next set of data, and what you want to do is you want to use just your calculator to compute all these different things. At the top we have the mean, median, and mode. That would be your measures of center. The rest of these are your measures of variation. You have your 5-number summary, and you have your range and your standard deviation. Now, on a separate recording, I have how you do these things. If you'd like to practice them, feel free to do that here. I'm putting the answers to all these on your slide. Make sure before you come to the test that you do know how to do all of these. What I want to say, and part of the reason that I have this on here, if we compare our range and standard deviation, on stock A the range is only 11, meaning from the smallest stock price to the highest stock price there's only a difference of 11. The range is 57, so this stock has a lot more variation in the price. But without looking at the standard deviation, it's hard to tell. Is that just because we started out with an extra low price, or did we reach an extra high price? And how did the rest of the data fall in between? That's what the standard deviation is good for. The standard deviation is essentially an attempt to describe the mean difference between each data value and the mean. Now these two sets of data had the same mean, so they had the same middle. So if I had a middle, a mathematical middle of 61.5, on stock A, what I'm saying is if I took the difference between each data value and the mean, the average distance would be 4.5 units. So 4.5 units is how far the average distance is between each data value and the mean. What does this one say? The average distance between each data value and the mean is about 18 1/3. Compared to 4, 18 1/3 is a lot more spread out. So not just the bottom and the top number are spread out for data set B. All the data is much more spread out from the middle than it is for stock A. So that's a small explanation of what the standard deviation is. The bigger the number, the more all the data is spread. The smaller the number, the more clumped up it is around the center.